The Merriam-Webster English Dictionary defines the word funky as, quote, having an offensive odor. Systems of equations, of course, are math. They have no smell. And if they did, they would obviously smell amazing. So I personally take offense to this definition. As an alternative, Merriam-Webster suggests that the word funky can be used to describe something, quote, unconventionally stylish, or being, quote, odd or quaint in appearance or feeling. Maybe that's not better, but it's good enough for our intents and purposes. We're gonna roll with that definition and see, just like we did for equations, inequalities, and absolute value, just how odd, quaint, and or unconventionally stylish we can get when we encounter some funky systems of equations, our 7th class of Unit 5. The idea, of course, is that usually when I'm solving a system, I'm able to get a relatively nice answer. No matter which method we choose, between substitution or combination elimination, as long as we know what to do, we shouldn't run into too many issues finding that answer. Take, for example, this guy. X minus 2y equals negative 2, 3x plus 4y equals negative 11. I've told you to solve, but I, notice, have not specified whether to use elimination or substitution. That means that you have the choice. You can do either one, whichever you prefer, whichever makes you happiest. Of course, both of them make you happy because all math makes you happy, but you're gonna pick one of the two, whichever you prefer, to find the values of x and y. Take 2 minutes, pause the video, see how far you get. Can you get me x and y? Go ahead. And stop. So I want to get x or y first using either substitution or elimination. Because it's been a minute, I'm going to do this using substitution. Don't worry, we'll get practice using both. Notice in the first equation that I've got x with a coefficient of 1. That tells me that substitution is going to be relatively easy to do. So I'm going to take that first equation, let me rewrite it off to the side here, x minus 2y equals negative 2. To get x by itself, I'm going to add 2y to both sides. That tells me that x is equal to 2y minus 2. From here, knowing that x is the same as 2y minus 2, I can take that value of x and substitute into my bottom equation. So now I know that 3 times x, but we've just established that x is equal to 2y minus 2. So by substitution, 3 times 2y minus 2 plus 4y is equal to negative 11. From here, let's do some distributive property. 3 times 2y is equal to 6y. 3 times negative 2 is equal to negative 6. I'll carry down my plus 4y equals negative 11. From here, I've got some like terms I can combine. I have 6y plus 4y. That's going to give me 10y's minus 6 equals negative 11. To get y by itself, next move, let's add 6 to both sides. 10y is equal to negative 11 plus 6, which is equal to negative 5. Last move, we'll divide both sides by 10 to show that y is equal to negative 1 over 2. Knowing that y is equal to negative 1 over 2, I just need to find the value of x. Thinking caps, where's the wisest place to substitute this value of y back in? 5, 4, 3, 2, 1. My goal is to get x by itself. Notice I've got an equation with x by itself right there. So I'm going to take this equation, x is equal to 2y. Y we've established is negative 1/2 minus 2. There we go. 2 times negative 1/2 is negative 1. And negative 1 minus 2 is equal to negative 3. As an ordered pair, how would I write this? 5, 4, 3, 2, 1. Very nice. X comes before y in the alphabet. Therefore, in my ordered pair notation, the negative 3 would come before the negative 1/2. So, if you wanted to, you could have done this by elimination. You should get the same answer either way, but notice we got an answer, which means you should probably expect something like that to maybe not happen, or at least not happen quite so nicely for the problems that are going to follow. Take a look at this guy. Will our solutions, or the process of finding our solutions, always be so nice? Well, probably not. 4x minus 2y equals 8, 2y minus 4x equals 6. Let's try and solve this together. So, we did substitution up above. I might want to do elimination here. Why do you think elimination might be a good move here to make? 10 seconds, pause the video. And stop. So notice I've got 4x and negative 4x, for example. I've got negative 2y and positive 2y. If I do some elimination, maybe I can get to a place where I can get some variables to cancel out. So I am going to add both of these equations together. 4x plus negative 4x, that is equal to 0. Negative 2y plus 2y, that is equal to 0. So the left side of my equation is 0, and 8 plus 6 is equal to 14. But 0 is not equal to 14. Notice I've gotten to a place where all of my variables have gone away. So I'm a little confused. I need to figure out what the heck is actually going on here. Well, to help me make sense of what's happening, it might behoove us to think about what we're actually doing by solving a system. Remember, when I'm finding the solution to a system, mathematicians often forget what they are actually identifying. What does the solution to a system tell me about the equations in the system? Look back at your notes, take 30 seconds. What am I actually finding here? Go. And stop. Hopefully you've got this down in your notes. If you took good ones, you definitely should. The solution to a system, all the way back in Unit 5.2, we said that a solution to a system is actually the point of intersection for the lines in our system. It tells us where the lines intersect. So, if I'm thinking about how pairs of lines on the same plane might interact with each other, there are 3 different options if I'm placing any 2 lines on the graph for how they might interact. What do you think those 3 cases might be? Take a minute, pause the video. Take a risk, take a chance. No right answers here. There is kind of a right answer, but what do you think some of my options for the way that 2 lines on the same graph might interact with each other could be? Go. And stop. So, for the normal types of systems that we've been working with up until this point, we know that we're finding a point of solution. So it is a point of solution, a point of intersection. So it is entirely possible that our lines, no matter what they look like, maybe they're even perpendicular, but they could intersect at a single point. So if I have a single point of intersection, as we know, as we did in our first example, a single point of intersection tells me that my system should have exactly one solution. If you're interested in some fancy mathematical terminology, a system of equations with one solution is called a consistent system. We can consistently expect to find a solution to our system. But if we think about other ways that pairs of lines might interact, one special interaction that we talked about at the end of Unit 4, what happens if I have 2 lines that are never going to intersect? In other words, the fancy word for lines that intersect at no point. They do not have a point of intersection. These lines are called 5, 4, 3, 2, 1. Very nice. These lines are parallel. So it is possible that my lines might be parallel. So notice, if I have one point of intersection, I have one solution. But if my lines don't intersect, there is not a point of intersection, what does that tell me about the solution set? Well, a solution is a point of intersection, and if there are no points of intersection, there are no solution. So this system of equations would have no solution. Thinking cap. A system of equations with a solution is called consistent. What do you think that means that a system of equations with no solution would be called? Alrighty, well, the opposite of consistent, I would say that it is inconsistent. So an inconsistent system has no solution. And finally, this one is a little bit wonky. What if I had two lines? They're actually not going to be parallel, but what if my two lines happened to have the same slope, but to also have all of the same points? In other words, it's possible that my lines could intersect at one point. It's possible they could intersect at no points. It's also possible they could intersect at more than one point. But if they're going to intersect more than once, they in fact need to intersect at every point. What that tells me here is that if my lines intersect at every point, what's really happening here is that my lines are the same. They're just two different ways of writing the same equation. So, if a line intersects at every point, it has infinitely many points of intersection, perhaps unsurprisingly. This system of equations would have not one, not none, but infinite solutions. Here, any point on the line would also be a point on the other line. This guy is called a dependent system, if you're interested in some math terminology. It is also technically a consistent system because it does have a solution. But we call it dependent because the equation of one line depends on the other. So these are our three cases for the types of systems that we might encounter: consistent, inconsistent with no solutions, and dependent with infinite solutions. So again, scrolling back up here, I ended up in a position where 0 is equal to 14. That is not true. To solve means to make something true. So what do you think happens to be the case for this pair of lines? What kind of solution set do they need to have? 10 seconds, pause the video. What do you think its solution set is? Go. Alrighty, well, if I'm trying to solve it, I need to make it true. 0 is not equal to 14. This statement is not true. And if I have a statement that is not true, that tells me that I should have a system that is unsolvable. It has no solution. So this is an example of an inconsistent system. There is no way that I could find any ordered pair x comma y that would make both of these equations true simultaneously. They would be parallel to each other. Fantastic. Let's see if we can apply this idea to some other examples. Let's take this friend. 5y minus 3x equals -6. 6x minus 10y equals 12. Can you tell me, is this going to be consistent, inconsistent, or dependent? And if it is consistent, can you find me the point of intersection? Go ahead, either combination or elimination. Let's see what type of system we're working with. Go ahead, 2 minutes, pause the video. And stop. Let's do, for the sake of switching it up, some elimination. So I'm going to take the first equation here. Notice I have a 3x on top and a 6x on the bottom. Let me multiply the top equation by 2 to turn 3x into 6x. Taking this guy here, my new system of equations on top, 2 times 5y would give me 10y. 2 times -3x is -6x. And 2 times -6 is -12. And then on the bottom, I've got 6x minus 10y equals 12. In order to do some elimination here, I probably want to add my two equations together. When I do that, 10y minus 10y, well, these guys are going to undo each other. I've got negative 6x plus 6x. These guys are going to undo each other. And then I've got negative 12 plus 12. That is equal to 0. Both sides of my equation are equal to 0. What does that tell me about my solution set? Well, this is always true. If I end up with a statement that is always true, as we've seen time and again, what does that tell me about my solution set? 5, 4, 3, 2, 1. Well, if it's always true, that means any point on these lines would work. There are infinitely many solutions. So this guy is an example of a dependent system. These lines are, in fact, the same line, as you can see from above. Fantastic. Let's do 2 more for the road. Lock in the skill. Negative 2x plus y equals 3, negative 14x plus 7y equals 21. Tell me, is this consistent, inconsistent, or dependent? If it is consistent, let's find its point of intersection. Go ahead. Let's find x and y. And stop. So here, I'm going to do some substitution. Again, you can do it either way. It does not matter. Notice that I have negative 2x plus y is equal to 3. If I take 2x and add it to both sides, I can get myself in a position where y is substitutable. Y is equal to 2x plus 3. Let's take this guy and sub in to our bottom equation. From here, I know that negative 14x plus 7y, but we've just established that y is equal to 2x plus 3. This is equal to 21. From here, let's do some distributive property. So I've got negative 14x plus 14x plus 21 is equal to 21. Notice on the left side, negative 14x plus 14x, well, that is 0. So I'm left with 21 equals 21. Now that I'm here, I need to ask myself, is this true? Well, yeah, 21 is equal to 21. What does that tell me about my solution set? A statement that is always true has infinite solutions. If it ain't broke, don't fix it. And it ain't broke yet. So this guy is another dependent system. Last one, let's try x plus 2y equals 1 and negative 1/2 x minus y equals 4. Use either substitution or elimination, whichever you prefer. Go, go, go. And stop. So, last one we did substitution. Let's do elimination here. So, notice I want maybe to turn y into 2y. I'm going to take the bottom equation. I'm going to multiply everything by 2. So I'm going to take each of my terms here and multiply by 2. When I do that, I get on top x plus 2y equals 1. And on the bottom, 2 times negative 1/2 is negative 1. So I've got negative x. Negative y times 2 would be negative 2y. And then finally, 2 times 4 is 8. Using combination, let's add our two equations together. Notice x plus negative x, that's 0. 2y plus negative 2y, that's 0. So this whole side is equal to 0. And 1 plus 8 on the right is equal to 9. 0 is not equal to 9. Therefore, what does this tell me about my solution set to my system? 5, 4, 3, 2, 1. So this is going to be an inconsistent system. It has no solution because we've arrived at a statement that is fundamentally false. These lines are parallel to each other.